Okay gang, our next topic is entitled Constant Acceleration, but you're probably mostly going to end up referring to it as SUVAT questions, and that's probably what they're going to talk about it as in maths as well, just to keep you from being confused, and you will see why very, very quickly. So, this is all about the equations of uniform acceleration, and I cannot say often enough that this is for uniform acceleration. So we can only use these equations, when there is no change in the acceleration. So the acceleration is just a constant. Okay? So symbols we're going to use a lot, and you're going to need to get into the habit of using. So V is for the final velocity of an object. U refers to the initial velocity. A is the acceleration. T is the time that the change is happening over, and S is the displacement during that change in velocity. So you rearrange those and you find the word SUVAT. I say word SUVAT, but you can see why we call it that. So there are some equations. Now for maths you are going to have to memorise these. For physics they will be in your data book. So the equations are as follows. V equals U plus AT. V squared equals U squared plus 2s, S equals a half U plus V times T, and S equals UT plus a half AT squared. Now, this one here, this third one, I will probably never ever use it. You can always manage with just the other three, because that one's a little bit awkward. You can use any of them, there's no problem, but this one you probably will find you won't use very often. Just to give you a heads up on that. But as I said, for maths you are going to have to learn all of these. And as I said before, we can only use these equations if the acceleration remains constant. If the acceleration changes at all, these equations no longer work. So it's only for constant acceleration. That's really, really important. Okay? Right, so I've just pulled these equations out of nothingness, but I didn't really, they did come from somewhere. And they came from looking at velocity time graphs specifically. Well, two of them did, then we just rearranged to get the third and the fourth. So you can be asked to show where these equations came from. So let's have a look. So I've just got a velocity time graph here, and I've got an object that started with a velocity of u, and we can see that it's accelerated in a constant manner because it is a straight line. And I'm just going to be interested in this section here. Now, we know that from a velocity time graph, the gradient of the line gives you the acceleration. So the gradient of the line would be the change in y divided by the change in x. So the change in y, while this change in acceleration is happening, is v minus u. That would give me this distance here. And the change in x is the time. So it's just time t that we would read off here. So that gives me that a equals v minus u over t. So I can then rearrange that. So if I just bring t over to the left-hand side of the equation, that gives me that at equals v minus u, which is going to be useful later on. So I know that this side, v minus u, is also equal to at. If I keep rearranging, I get to v minus u equals at, and eventually v equals u plus at, which was our first equation. Right, the second equation that's most useful, I know it was fourth on the list, but it's the second one we're going to find. It is the most useful one, this one. And this comes from the fact that the displacement is equal to the area under a velocity time graph. So that's something that we know already from kinematics. So if we have a look at how we would calculate the area under this velocity time graph, the easiest way is to split it into two shapes. So the rectangle here, and then the triangle here. So the way I'm going to find the area of the rectangle is easy. It's just going to be this distance here times this distance here. So x distance is time, and on the y it's u. So that first rectangle is ut, which gives me this part of the equation. Find the area of a triangle. It's half base times height. We showed earlier that the height of this triangle is equal to AT, and the base is T. So a half times AT times T is a half AT. So the total area underneath is UT plus a half AT squared. That gives me the displacement. Easy peasy, right? So the only other one they'll ever ask you to show was that the third one that I showed you was useful. So v squared equals u squared plus 2as. So I'm going to show you where that comes from. And it's just from playing with algebra, really. And this is something you do need to get comfortable with. So here we've got v equals u plus at. So that's the first equation we proved where it came from, so we're happy with that one. So all I'm going to do to start with is square it, because that gets me to v squared, which is what I'm ultimately trying to get to. So then I'll just square out the brackets. So v squared will therefore be u squared plus a squared t squared plus 2uat, which looks disgusting. So all I'm going to do is see if I can make this bit look a little bit nicer. So what I'm going to do is I'm going to pull out, oops, it helps if I press the right direction. I'm going to pull out 2a from this. Okay, so that's going to leave me with taking the 2a out of here, which gives me ut left. And by pulling 2a out of this one, it leaves me with a half at squared. Okay, because I've multiplying by 2, so I have to divide this by 2, and I've taken an a out, so that leaves it at half at squared. If I then substitute equation 2 in, because the second one that we proved was ut plus a half at squared equals s, I can substitute that in for this whole bit here. So that leaves me with v squared equals u squared plus 2as. So those are your 3 equations that we need to show where they came from. We're going to practice using them a lot. These are going to be a big chunk of what we're going to do in our mechanics topic. So we will get lots of practice, don't you worry. Now, there's one more thing we just need to look at, and this is a specific experiment. We are going to do a version of this one, but it's something that you do need to know about. And it's methods for determining the value of g, so the acceleration due to gravity. So that value that we looked at that was in your data book, the one that has 2 units. But the most useful one is meters per second to the -2, because it is an acceleration. And obviously the acceleration due to gravity is a constant acceleration. So often when we're looking for things with constant acceleration to do calculations on, things falling because of gravity are going to be a very useful place to look. So a method to try and calculate the value of g experimentally is outlined below. So basically what you do is you set up a circuit where you've got a steel ball that's held in place by an electromagnet above a trapdoor. As soon as the electromagnet turns off, that starts a timer. And that means that you start timing, obviously. Duh. You know what, I'm not even going to edit that out, it's fine. The electromagnet turns off, steel ball drops, timer starts. The steel ball then falls until it hits the trapdoor. Once it goes through the trapdoor, that stops the timer, and you have therefore recorded the time it's taken for the ball to go from 0 till it is passing through that trapdoor. That gives you a distance of h, so that gives you the distance fallen, and you know that it started with an initial velocity of 0. So that means u equals 0, s is equal to the distance fallen, or h as it says down here. So once you've got your initial velocity as 0, if you use the equation s equals ut plus a half at squared, the ut will vanish because your initial velocity was 0. So that means that your displacement is equal to a half at squared. Now the a is what we're trying to find. We can measure the h because that's the distance between where the ball started and the trapdoor and the time we recorded. So this is a method for determining g, the acceleration of freefall. Now obviously you don't have to do it with the electromagnet and the trapdoor. You can just drop objects and use the same theory. But this is a specific method that you could be asked about, so it's one that you just need to make sure you've got firm in your heads. We are going to do some practicals on this in class, so you will calculate it for yourself. And we will also at the same time talk about issues with why the number you get is very unlikely to be 9.81. And that's something that you can be thinking about before I see you next. Right, that is it for today. Sorry for the mess ups, but you know, makes it more interesting, right? Keep telling myself that anyway. So remember, any questions? Not that any of you ever seem to have any, but if you do, remember to ask them when you see me.